This is Lab 5, Magnetic Braking using Faraday's Law. In this experiment, I calculated the speed of a magnet that fell through aluminum foil, which is a strong conductor, in order to calculate the magnetic field and the magnetic flux of the magnet as it passes through, and the induced current produced in the aluminum foil as the magnet fell. The physical quantities for the lab are shown in the top left-hand corner. The length of the foil was 0.03 meters, width was 0.005, and a radius 0.0125 meters, and from Lab 3, we know the magnetic moment was 1.584 times 10 to the negative fifth. Using the following equations, I was able to calculate the values for the different circumstances. Magnetic field was calculated using the following formula. The change in flux, or d flux over dt, was calculated to be this. Induced current was also calculated as the change in flux over the radius, which is simply using the change in flux formula and multiplying a radius in the denominator. All the numerical values are as listed. Here we have more calculations. The Biot-Savart law is used to calculate the magnitude of the force on the aluminum foil, and the equation is shown as listed. Note that since the computer code cannot do a cross product, sine of theta is used instead to represent a cross product between B and I. And on the bottom we have Newton's third law, which says that the sum of forces has to equal and be zero, or mass times acceleration. In this case, the sum of forces was the force of magnetism plus the force of gravity, where gravity is calculated to be mass times gravity, and is in the negative direction. Here's the computer code, or snippets of it, that show different formulas. On the top left, we have the magnetic field formula, which is used as a function. Underneath that, we have how to calculate the change in flux, which is also used as a function in the computer code. Then there is the magnetic force and the net force, which are both using the Biot-Savart law and Newton's third law. And finally, on the other side, we have the current calculator, which uses a function to calculate the change in current, and we have the force of gravity, which again is simply gravity times mass in the y direction and is negative. Here you can see all the trials of the magnet being dropped through the aluminum foil, with an average of about 0.8 seconds for it to hit the bottom. Here we have different ways to interpret the simulation. First is the current colors. As the magnet is falling, underneath the magnet, the current is flowing in the counterclockwise direction in order to induce a current upwards. This is because current is induced in a direction that will make a magnetic field that opposes the change in magnetic flux. So, when the magnet is falling, the magnet is increasing a downward magnetic field. So, current must increase an upwards magnetic field, meaning current is counterclockwise. And when the magnet passes that section of foil, the current then switches to be clockwise to account for the change in magnetic field. Second, if you were to flip the magnet, that is, flip the north and the south pole in the magnet, the currents would flow in the opposite direction. This is because, once again, current flows to counteract the magnetic field, and so if the magnetic field were flipped, current would have to flip in order to counteract the change in magnetic field. Number 3. When looking at the simulation time, it was a fairly accurate time. The simulation showed about 0.25 seconds, which was a lot faster than in real life. In reality, we have to account for several other factors that slow down the magnet's speed, including drag, which is air resistance as the magnet is falling down the tube, and the Earth's magnetic field, which is another magnetic field that can interfere with the induced current in the foil. These two factors meant that the magnet in real life falls a lot slower than the magnet in a simulated reality, and that is why there is a discrepancy between the two times. And number 4, the forces are balanced. When looking at the distance versus time graph on the simulation, you can conclude that the forces are balanced because the distance versus time graph is linear. There is no acceleration. This means that the magnet has reached terminal velocity, and will neither continue to accelerate nor decelerate because the forces of magnetism and gravity are balanced. Some what-ifs. If the resistivity of the aluminum foil was in reality close to zero, then the magnet would fall very quickly or very close to real speed without a magnet. Because with nothing to slow down the magnet, the model would break. And with nothing to slow down the magnet, then the magnet would fall very close to the normal speed. Furthermore, if there were holes in the tube, the magnet would fall faster because less rings of full current, or less rings of tubing in the aluminum foil, would mean that there is less current holding the magnet up or slowing it down. In conclusion, I use magnets in real life and a simulation in a computer to calculate the magnetic field and gravitational force.